Okay, so let's continue along with chapter 7. So we've already seen simplifying rational expressions. We've seen multiplying and dividing them, which is really similar to simplifying. The big thing is factor, 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 so that you can cancel things out. Now we're going to get into least common denominators, which hopefully sounds really familiar. When we're adding and subtracting regular fractions, you still need least common denominators. Same thing with rational expressions. So before we actually start adding and subtracting rational expressions, we're going to need to know how to find a least common denominator, which is what we're going to do in this section. And then 7.4 is when we'll actually add and subtract them. So just like we've been doing, first thing I'm going to do is go back to just regular old fractions. And if we look at an example, we're going to go ahead and find the LCD. Remember, LCD is the least common denominator of, let's do 2/9 and 5/12. So normally what we do is we can look at the multiples of these numbers down here. So I could list out 9, 18, 27, 36, 45. We could keep going. If I go ahead and list out the factors of, or the multiples, sorry, of 12, we have 12, 24, 36, and you want to stop when you find the smallest number that they both go into. And notice that this number, our LCD, is always bigger than the numbers that we started with, unless the number were to be one of the numbers that we started with. So it's either exactly what we started with or bigger than what we started with, but never smaller. So our LCD for this one is 36. Now, some kind of behind the scenes work that we could do to find the LCD, but we don't normally because it would make these ones a little bit more complicated, is factoring the numbers. So what I mean by that is 9 is equal to 3 times 3. And 12, if I were to break this number up into its prime factors, I'll break it into 2 and 6, and 2 is prime, and so I'll break 6 into 2 times 3. So 12 is equal to 2 times 2 times 3. Oops. All right, so what we're going to be doing when we look at rational expressions is we want to see what different factors we have. So in this one, we have 3's in the first one, and then in our second number, we have 2's and a 3. So we have two different factors. We have a 3 and a 2, and we want to multiply the factors together the most number of times they occur. So what I mean is, if we look at the 3's, we have 2 3's in this first one, 1 3 in the second. So the most number of times they occur is 2 times. So we're going to have a 3 times 3. And then with the 2's, the most number of times these 2's occur is 2 times. We have 2 of them in the second number, none of them in the first number. So we still have to include them because they appeared in the second number here. So we're going to multiply this by 2 and 2 again. And now if I were to go ahead and multiply all these together, 3 times 3 is 9, 9 times 2 is 18, 18 times 2 is 36. So we get the same number. This way it's just a little bit more complicated for numbers, but this is what we're going to be doing with rational expressions. And it would be the same thing if we had 3 fractions here. So just remember, if you're finding the LCD for 3 fractions, you're finding the smallest number that all 3 of those numbers go into. So let's go ahead and I'm going to first write out kind of directions for finding the LCD. Not the LCP, the LCD, with rational expressions. So if you see regular fractions like 2/9 and 5/12, you definitely do not have to go through and factor those numbers. Just do it the normal way. Sometimes you can tell just by looking at the numbers. With rational expressions, we will have to factor though. So keeping that in mind, first thing we're going to do is factor the denominators. And notice how we're finding the least common denominator. So I don't care what the numerator is. You can completely ignore the numerator, just focus on the denominator. Second step, we're going to list each factor, the most, that's really important, it's the most number of times it occurs in one fraction. So big thing to keep in mind here is if we look back at our example with the numbers up here, even though we have 3 3s all together, we only want the most number of factors, or sorry, the most number of times each factor occurs in just one of these fractions, not both of them combined. And then lastly, the last thing that we did up here was just multiply those numbers together. That's what we're going to do here. We're going to multiply these factors to find the LCD. And when you're doing this, we're going to end up with some that might be a little bit more complicated. They might have groups with like an x plus 4 and then an x minus 3 that might be squared. And they're going to get pretty long. We're not actually going to multiply these out. We're going to leave it in factored form. One reason is that saves you a little bit of time. And secondly, when we start adding and subtracting these fractions together, we're going to simplify at the end, which means we're going to want stuff factored so that we can cancel things out. So always keep your denominators factored. Okay, let's go ahead and jump into some examples. So we're told to find the LCD. And we're going to start off with some easier ones where we don't have to factor, but we're still going to be working with variables. So let's take a look at 1 over z to the 4th and 3 over z to the 6th. So there's no factoring we can do because we only have a single term on the bottom of each of these fractions. Now we want to move on to step 2, which said to list each factor the most number of times it occurs in one fraction. So our different factors here, we actually only have one. We have a z that appears in the first and second fraction. The most number of times it occurs is 6 times. So remember, we're looking for the most number of times in one fraction. So our LCD is z to the 6th. So you can think highest exponent. So it's kind of the opposite of when you're factoring. When you're factoring things out, you take out the lowest exponent. When you're finding the LCD, it's the highest exponent. Okay, let's try another one. 7 over 20p and 11 over 30p. So again, first thing you want to think is, can I factor these? Well, they're single terms. There's only multiplication, no addition or subtraction. So no, we can't factor. Now, if we break it down into the different things that we see here, we have numbers in the front, we have coefficients, and we have a variable that's the same in both. If we look at the numbers first, what is the LCD of 20 and 30? If those were our denominators, What is the smallest number that 20 and 30 both go into? They both go into 60. Remember, this number should always be at least as big as these two numbers, should never be smaller. And if you're ever unsure about what that number is, remember you can list out the multiples of these. So 20, 40, 60, 30, 60, 90, and the smallest number they have in common is 60. All right, so we're done with the coefficients here. Now, if we look at the variables, we have a p in each of these. So the most number of p's we have in one fraction, well, we have 1p here, 1p here. So our LCD needs only 1p. That is the most we have in one fraction. All right, let's try number 3. Got 4 over 16 m cubed n and 5 over 8 m to the 5th n squared. Okay, so again, let's first see, can we factor? Well, we have single terms, so no, we can't. Now let's go ahead and look at the numbers first. So we have a 16 and an 8. So what is the smallest number that they both go into? Well, in this case, it's going to be 16. So this number still isn't smaller than either of these, but it is exactly 16, which is fine. And now if we look at our next variable, so we have an m in each of these, and then we have n. So we're going to focus on these separately. If we look at the m's first, the most number of m's we have in one fraction. We have 3 in this first one, 5 in the second one. So the most in one fraction is 5, so m to the 5th. And again, just your highest exponent. And then our n's, we have 1 n on the left, 2 n's on the right. The largest number of n's is 2. These hopefully will get a little bit easier as you do them. You'll kind of get into the habit of just seeing, oh, the highest exponent, that's this one. Okay, number 4, I'll go ahead and put it up here. Number 4, we have 3 over 25a squared and 2 over 10a cubed b. All right, so take a look at the numbers first, because again, we can't factor these single terms. So if we're looking at the numbers 25 and 10, what is the smallest number that 25 and 10 both go into? Well, if we think of the multiples of 25, goes 25 and then 50. And 10 also goes into 50. So that's our least common multiple of 25 and 10. And now if we look at our variables, we have 2 a's in the first fraction, 3 a's in the second one. So how many a's do we need in our LCD? Well, we need the largest number, so we need an a cubed. And then lastly, we have 1 b in the second fraction, but no b's in the first fraction. So the largest number of b's we have is 1b. That's the difference between LCD and when you're factoring, is if one of these fractions has a factor, but the other one does not, we have to include it in the LCD because that is the largest exponent. All right, number 5. 7 over 3a and 11 over a squared minus 4a. All right, so this is the first one here where we actually have a denominator that we can factor. So first fraction here, nothing we can do, it's a single term. So we'll leave that one alone. But if we look at our second denominator here, we have an a squared minus 4a. So first things first, is there anything we can factor out of both of these terms? Yeah, we can factor out an a. And then we would be left with an a minus 4. And I'm going to go ahead and bring this first fraction down too, so we can look at them right next to each other. All right, so now that second fraction has been completely factored. Now let's look at our different factors. We have a 3, and the other fraction doesn't have any coefficients. It doesn't have a number in front of this a. So that means we just have to include this 3 because we have one factor of 3, and that is the most we have of that factor. Now let's look at the a's. I'm actually going to color code this. So we had one of those 3's. We have one a in each of these, which means we want to include how many a's? Just one of them. And notice how I'm not paying attention to the a that's inside this parenthesis. That is because this a minus 4 is its own factor, that entire group. So anytime you see those parentheses, that means that this is one factor, and we're going to just consider the stuff inside that parentheses for that factor only. So the a that's inside doesn't get counted with these a's. So keeping that in mind, that is our other factor here. We only have one of these a minus 4. It doesn't show up in the other fraction, but we do need to include it. So we're going to include a minus 4. And that's it. If you wanted to leave it just like this, that's perfectly fine. And that's actually the better option. You can distribute, but I do not recommend doing that because you're just going to have to refactor anyway. Okay, let's go ahead and try 2 more examples. Number 6. This one we're given 3 fractions. We're given 1 over x squared plus 7x plus 12, 2 over x squared plus 6x plus 9, and 5 over x squared plus 2x minus 8. All right, so what is our first step anytime we're working with rational expressions and especially with least common denominators? We want to factor. So let's go ahead and factor each one of these. Notice they're all pretty nice trinomials. That means we're going to use the big X if that's what you like to use. If you just want to go ahead and find your 2 numbers, not using the big X, that's fine too. But these are each going to become 2 sets of parentheses. So in this first one here, we're multiplying to 12 and adding up to 7. Think of your factors of 12. We have 1 and 12, 2 and 6, and 3 and 4. And those are the numbers that add up to 7. So we're going to have x plus 3 and x plus 4. In our second fraction here, we're going to be multiplying to 9, adding to 6. So 9, we have 1 and 9, or 3 and 3. 3 and 3 add up to 6. So we have x plus 3 and x plus 3. You should see some kind of common factors between the 2 of these so far. And then lastly, we're multiplying to a -8 and adding up to 2. Now, multiplying to a negative means we need a positive and a negative. So we either have 1 and 8 or 2 and 4. We're adding up to a 2, so our difference is going to be 2, and this 2 will be the negative one. So -2 and 4. x minus 2, x plus 4. Again, one of them is common, or it has a factor in common with the first fraction here. All right, now that we're completely factored, we can go ahead and look at the different factors that we have. So if we go ahead and look at, let me change the color here. Our first factor, I'm just going to work from left to right. And kind of underlining as you go. It doesn't have to be different colors. You could do like a single and a double, and then some kind of other underline. That way you know that you're taking care of all the different factors. You don't kind of lose any. I would recommend doing that. I'm going to use different colors. So if we look at our first factor here, we have an x plus 3. We have one of them here, two of them here, and none of them over here. So what is the most number of times an x plus 3 occurs? Twice. It occurs twice in the second fraction. So we're going to do an x plus 3 times x plus 3. And I'm actually going to condense that down to an x plus 3 squared, but either one would work. Next, we have an x plus 4. And then we also have an x plus 4 on the right over here, but we don't have one in the middle. So the most number of x plus 4s we have in one fraction, 1. We have 1 over here and 1 over on the right. So we need 1 x plus 4. So I'll add that to both answers, showing you can do it both ways. And then lastly, we do have one more factor here. We have an x minus 2. And that only occurs once altogether. It doesn't occur in either of the other fractions, but we do need to include it. So we're going to have an x minus 2. All right, so again, you can write it as this. You can expand out that x plus 3 squared, or you can leave it as x plus 3 squared. All right, let's go ahead and do one more before we get to the last little part of this section. Let's do 6 over 5m and 4 over m squared minus 3m. So now that we've gone through and we've done 6 of these examples together, I would recommend pausing, trying this problem by yourself, see how well you could do it, following through the steps, and then check your answer with mine. So to get started with this one, again, first thing you want to do is check to see if we can factor. We can't factor this first one, so I'll leave that as 6 over 5m, but we can factor m squared minus 3m. This is only 2 terms, so it's not a trinomial. We don't want to use the big X, but we can factor out an m, and we're left with an m minus 3. So now, if I go ahead and look at the different factors we have a 5 that occurs in the first fraction. That is the only place it occurs, so I'm going to include 1 5. And then we have an m that occurs once in both fractions. And it's just 1 time each, so we're going to include 1m. And then what is our last factor? This m minus 3. And again, we only have 1 m minus 3 here, so we're going to include 1 m minus 3 in our LCD. Okay, so that is our first step that we're going to need when we're adding and subtracting rational expressions. The other thing we're going to need is writing equivalent expressions. So let's go ahead and take a look at that. And again, it might not sound like something you've seen before, but we definitely have. This is something else you use when you're adding and subtracting regular expressions, or sorry, regular fractions. So let's say that we were adding 3/4 together with another fraction, and that fraction has a denominator of 36. So when you're adding and subtracting fractions and you have to change the denominator, this is where writing equivalent expressions comes into play. Because what we're going to do is we're going to take 3/4 and we want to write it as an equivalent fraction with a denominator of 36. So what we need to do is figure out how we get from a 4 to a 36 so that we can do the exact same thing to the 3 on the top, because we don't want to actually change the value of this fraction. So to get from a 4 to a 36, we're always going to see what we're going to multiply by. We need to multiply by 9. And what we do to the bottom, we have to do to the top. So 3 times 9 is 27. So 3/4 and 27 over 36 are equivalent expressions. And so we're going to do the same thing now with rational expressions. And so for these examples, we're told to rewrite the expression with the new denominator. So exactly what we just did with this fraction up here, except now we're going to deal with some factoring and a lot of variables. All right, but let's start off with one that's a little bit easier. Let's go ahead and do -3 over k. And we want to rewrite this with the denominator 9k. So first thing you want to do is factor first if you can. And then see what changed. So what I mean by that is if we look at our denominator that we were given here, remember in this first step, I don't care what the numerator is, we're going to deal with that in a second. We went from a k to a 9k. So our variables stayed the same, but we went from 1k to 9k. So what did we multiply by? We multiplied by 9. So what we do to the bottom, we're going to do to the top. And -3 times 9 is -27. So that first one, not too bad. We only had one little change and we didn't have to factor. Let's go ahead and try another one. This next one, we're given 7k over 5, and we want to write it with a new denominator of 30k. So again, first thing we want to do, because we can't factor with this one, we only have single terms, is see what changed. So one thing that changed is we went from a 5 to a 30. And how do we get from 5 to 30? Well, we multiply by 6. What else changed with this one? Well, we started off with no k on the left and we ended up with 1k on the right. So we also need to multiply by k. Now, if we go ahead and do that on the top, we're going to have 7k times 6k. 7 times 6 is 42. K times k is k squared. Now, if I wanted to check my answer, how would I do that? Well, if we look at the fraction that we ended up with and the ones that we started with, we should be able to reduce this down and end up with what we started the problem with. So 42 divided by 30, well, 6 is going to go into both of these. 6 goes into 42 7 times, so that's good. 6 goes into 30 5 times. So our numbers are good. And if we think about canceling out some k's, we can cancel out a k on the bottom, cancel out 1k from on the top, and we're left with just that 1k. So you can check by simplifying, but your final answer for these, at least for this type of question, is there'll be like a box on the top of a fraction and you'll type that one in. All right, let's try another one. For this one, we're given 9 over 2a plus 5. And we're changing this to something over 6a plus 15. All right, so one thing to notice here is that it's kind of hard to tell what has changed right now because we do have some expressions here that we can factor. So first thing we want to do is factor the denominators. And if we go ahead and factor, if we look at the first one here, there's nothing that 2 and 5 have in common, so we can't take anything out of there. But if we look at 6a plus 15, what is the greatest common factor of 6 and 15? Well, a 3. We can take a 3 out, and we're left with 2a plus 5. And you should notice that this looks really similar to what we started with. Now, we want to figure out how our denominator changed. They both have a 2a plus 5. And again, if you want to put addition and subtraction expressions in parentheses, because those are one factor, we can do that. So we started off with 1 2a plus 5, and then we ended up with 3 times 2a plus 5. So we multiply by 3 because that's what we're missing on the left compared to the right. So now if I multiply the 9 on the top by 3, 9 times 3 is 27. All right, and then one last example here. 5k plus 1 over k squared plus 2k equals something over k squared plus, sorry, k cubed plus k squared minus 2k. All right, so first things first, we want to go ahead and factor because this one is really hard to see how we get from the first denominator to the second. So if we go ahead and look at the first one first, we have a k in both of these terms that I could factor out. So we're left with a k plus 2. And then if I look at our second denominator here, first thing I can do with this one as well is take out a k. So if I take out a k, we're left with a k squared plus k minus 2. So we're not completely done factoring here. Even though we took out the greatest common factor, we can still factor this k squared plus k minus 2. So I'm going to go ahead and factor that out over on the right here. So this is a trinomial, so big X, multiplying to a -2, adding to a 1. The only things that multiply to 2 are 2 and 1. One of those has to be negative, and it has to be the 1. So we need a -1 and a +2. So we're going to have, now if I replace that trinomial with k plus 2 and k minus 1, and leave the k in the front, I'm going to cross these out so we don't get confused with those ones. But now we can see how we get from the first denominator to the second. So if we first see what we have in common, we have a k in both of them and a k plus 2. The only thing that we're missing from the first fraction is this k minus 1. So since we have to multiply this by a k minus 1, we're also going to multiply the top by a k minus 1. And so along the top here, we're going to have 5k plus 1 times, so I'm going to put that 5k plus 1 in parentheses, and then we want to multiply it by k minus 1. Make sure you put the parentheses around those first two terms there, because we are going to have to FOIL this out. And this is the only time that you actually want to FOIL things out. Because when we start actually adding and subtracting these fractions, we want to be able to combine our like terms on the top. The only way we're going to be able to do that is if we actually FOIL this out. But still leave your denominators factored. So I'm going to leave this factored down here. And then if I go ahead and FOIL along the top, one thing to note is that when you're doing the homework for this section, you could leave it just like this. I'm just going to multiply it out because when we get to 7.4, you're going to want to be multiplying these out. So just kind of get in the habit of doing that. All right, so let's FOIL. So 5k times k is 5k squared. 5k times -1 is -5k. And then we have 1 times k is a plus k. And 1 times -1 is -1. And then finally, I can go ahead and combine the like terms. So we have 5k squared minus 4k minus 1 over the denominator. All right, so now that we can find LCDs and write equivalent expressions, we can get into adding and subtracting rational expressions in the next section. So that's what we'll see in 7.4.